their dreams. Let me find my pen.
That kind of makes sense, but I can't see outright that it makes sense.
You might want to put the Tritanotopia filter on your game snap.
I do.
Oh, there you go. You've been doing it the whole time.
For like games.
Amazing.
Like
Amazing. Who needs to go to a doctor when you come to PCAM?
I learned I'm colorblind.
Very lightly. Well, I had a student who's a research student, Megan Crutchfield. She's really colorblind. She's red-green colorblind. She can't tell the difference between red and green at all. It's really fun to do my class with her because I do any colors. All right. So where were we? This is not our lecture. Oh yeah, it is our lecture. All right. So we were talking about springs, and I just want to recap a little bit about springs and why the hell we're thinking about springs today. Where the hell were we? Right. We want to start with vibrations, right? Geez, I think I just want to. I don't really want to go through too much of this. Okay, so, well, actually, let's do that. Let's recap. I think maybe I just get my brain in the right place. We're going to work with bonds. There was tackling the theory of vibrations of bonds. And the way we're going to do it is with springs. Springs kind of have all the nice properties that we expect bonds to have, other than, as far as we know right now, but springs can't break. So we got to kind of fix that eventually. But the idea is that a bond is a springy material that's got two parameters. Basically, a bond is described by two things. First is the stiffness of the spring K, the force constant. Like it tells you how much force you need to put into a spring to stretch it a certain length. So this is a spring of very low K. I barely have to touch it and it just spreads. All right. And then it's also what's called the reduced mass of the spring, which is the effective mass attached to the spring. And when we stretch a spring, you compress it, either expand it or compress it. It moves sinusoidally, right, as a cosine or a sine wave at a frequency omega, we call the harmonic frequency of the spring, which is determined by the square root of the ratio of the stiffness and the mass. So the stiffer the spring is, the faster it oscillates when you stretch it. The heavier the thing on the spring is, the slower it oscillates, and vice versa. Okay, it's kind of hard for me to show you the mass example of this spring. If someone would let me borrow their little spring, I'll take yours. It's dark colored. It's red, very red. Does that look like orange to you? No. Oh, okay. All right, so there's no mass attached to this spring right now, but we have gravity at it. Okay, so you can kind of think of gravity as a mass that installs, right? It's a fixed mass that installs a specific frequency. We're not changing the mass when we have gravity. It's constant, but the spring, the K, is fixed for this. So here's the equilibrium length of that spring. I just let go and gravity appends it, and this is where the spring wants to sit. So I'm going to stretch the spring. I'm going to let go, and we're going to see the spring oscillate up and down. It's going to damp very quickly because this spring is not a particularly good spring, right? It's going to bounce and then it's going to stop, right? But you can see that it goes like this. The first oscillation is very large in amplitude, and then it bounces off, and actually the collision causes it to damp out. But you can see that it bounces up and down at some frequency. If I add some mass to it, which I'll do with a pen or something. I have one in my pocket. You got a pen? Thank you very much. I'll add a mass to the end of the spring, right, to increase the frequency or the reduced mass of the spring. So we see the spring now stretches a little further because we've added a mass to it. So the equilibrium length is now longer. Mass is larger. And when I stretch it, we should expect to see that the frequency drops because the mass is larger, the denominator is larger in omega, so it should oscillate more slowly. Okay. See that? Sorry. Let's try it again. Let's try it with just the cap. Oh wait, that doesn't work. Right? It's not. Stay. No, that's going to make it even worse. No. No, eventually I'll just let you guys breathe. There you go. Now you can see it's oscillating. I won't. a little slower oscillation. Okay, so the same idea. Okay. Right, so those are the only two things that depend on the spring depends on. All springs are the same except for they have the same stiffness and the same reduced mass. They all oscillate in exactly the same way. Give me just a sec. I'm a little discombobulated because you guys got me distracted and I don't have all my notes up for today. I'll keep talking. So we talked a little bit about the motion of the spring, and again, the important thing that I want you guys to know, it's not a super important property, but it's good for comparison later on, is that there are these turning points. These are the maximum and the minimum extents of the spring, given the energy you put into the spring. Right, so the spring never exists longer than you stretch it, right? And the displacement from your stretch, the other side of the oscillation, when it compresses, the compression length is exactly the same as the stretching. Ideally, it just bounces back and forth symmetrically between the equilibrium length. It never goes longer than that. And that's just a consequence of the conservation of energy. And of course, this is a unique system compared to the particle in the box. And the particle in the box, inside the box, there's no potential energy. It's all kinetic. And here we have a smooth exchange between kinetic and potential energy. At the turning points, it's all potential and no kinetic, meaning the spring is stationary at those points. It's not moving at all. And then down here at the bottom, there's no potential, right? At equilibrium, kind of flies through equilibrium with maximum velocity and therefore maximum kinetic energy. Right, so a slightly different potential than the particle in the box, where we now have an exchange of two different types of energy. Right, and so we looked at that conservation and showed that the energy of the spring has to do with its stiffness and then how much you stretch it. Right, just like we thought before. And we started to look at this process of kinetic energy and potential energy in the context of the Schrodinger equation, our quantum mechanical version of the energy equation. And what we saw was that once you kind of work out the math for our harmonic potential for our spring, we have a wave function for our spring and we have this equation here that says that the second derivative of the wave function with respect to position gives us some number back minus the potential energy, x squared times psi. And I identified that that's very similar to the particle in the box. Particle in the box has, in some sense, half of the equation that we have for the spring. But the spring has this an additional term that's returned when you take the second derivative that's proportional to the distance. Because again, the second derivative of position with respect to the wave function is the kinetic energy. Kinetic energy has that proportionality, second derivative. And we know that the kinetic energy and the potential energy are exchanging depending on the position of the spring. So when we take a second derivative, we're kind of measuring the kinetic energy of the system in some sense. And what we get back is an energy, a total energy, minus the remainder, which is the potential. So that's the difference between a particle in a box and the spring, is that the potential energy can be some value, and that value depends on the position of the spring. So that complicates the math a little bit, but we have an idea. When I talked about the end of the last class, was that in some sense, if you ignore this, they're exactly the same. So there's like a wave-like property in our spring. The wave function is a wave function. It behaves exactly like we expect a traditional wave with no potential to act. But there's this additional fudging factor due to the potential. Okay, so I expect that there's some wave-like behavior here, but the actual behavior is not pure wave. It's not pure sine or cosine. It can't be, because if it were pure sine or cosine, the equation would look like this at the bottom. It'd just be particle in the box. So it has to be some other function, right, that has wave-like properties, but isn't a sine or a cosine. Right? And the guess that I made at the end of class was that we take the bell curve. The nice thing about, let me close this thing for Zoom quickly so we can see everything. We pick a bell curve as a guess because what we want is that when we take the second derivative of this function that we get some x's back. So if it were e to the minus kx, you never get an x back from the chamber. It just goes away. But here we get the x's back. Right? So when you take two derivatives, you take one derivative, you get an x out of the exponent into the chain rule. Do it again, you get x squared. Right? That's what we want. And I showed that this is a normalizable function, which is the first property that we need, meaning that it integrates to some finite number. So it can represent a probability, finite probability. And that this equation also satisfies our energy equation. Right? This is a valid wave function from the point of view of the Schrodinger equation, h psi is equal to a psi. You get back exactly what you want. When you take a second derivative, you get the wave function back times some number, which we can call the energy, minus x squared times our wave function times some number. Right? So even though the variables are a little different here, we can massage these equations here to match the equation. Right? So it satisfies the algebraic properties that we want, the calculus properties. But the problem that we saw at the end of class last time was that it's not orthogonal. Remember, the idea is that each energy level of a system are non-interacting with each other. If a molecule is in state 1, there's no probability you'll ever find it in state 2 or 3. Right? You localize the particle in a specific state, and it's there to stay. So when we calculate probabilities of where we observe a molecule in state 1 and ask what's the probability I then find it in state 2, that's this integral here. That's the Born probability rule. We integrate the square of the function. This should always be 0 unless the two states psi 1 and psi 2 happen to be the same state. Right? There's the probability that a system in state 1 stays in state 1 is 100%. The probability if it's in state 1 for it to be in state 2 is 0. And so when you go plug in this guess for the wave function, assuming different states, meaning different values of k, what we find is that you take a product of these two bell curves, and what you get out of it is another bell curve. So it's not like when you multiply a sine and a cosine together and everything cancels out because one odd and one even. Here, what you do is the Gaussian is a function that when you take the product of them, you get the same function back. So that means by definition that the integral of the product can't be 0 because the integral of one of the functions, one of the bell curves, and a product of two bell curves is one bell curve. So that means they're not orthogonal. Right? So they satisfy two of the three properties, which is better than we've done in the past with our guesses. But we have to build in that orthogonality. We got to make them have this property where they are even and odd, so that we can start to get this orthogonality, these zeros and ones. We want that even and odd symmetry with the function. All right, so what the idea is that, and this comes back to the idea that systems are waves. Wave functions are waves, and a bell curve has no wave to it. Right? It doesn't oscillate. But the bell curve does satisfy the algebraic property, but it doesn't oscillate. So what we have to do is to correct our guess by appending an additional function that inbuilds the oscillatory behavior. Basically, the Gaussian part is just half the answer. And in order to have multiple wave functions that are all orthogonal to each other, we have to add this oscillatory function that gives us the wave-like behavior inside the potential. And so what we would expect to see is that for some given state, on the outside of the potential, the system decays as a bell curve. But inside the potential, just like the particle in the box, it oscillates like a wave. That's very different behavior in the particle in the box, because in the particle in the box, the probability goes to 0 at the edges, at the turning points of the box. But here, it seems like not only is there non-zero probability outside of the potential, there's actually a decent amount of probability outside the potential. You can even calculate how much probability there is. So this is not a particularly sealed box. Right? It's a little leaky, right? And it's exponentially leaky, decay, negative exponential, so it decays very rapidly. But it's a leaky box by definition. So what we need to do, I'm not going to do it, I'm just going to show you the answer. It's how to embed this oscillatory function into this function to get a correct wave function. So we just need to do that last step. Now I need my new notes. Okay. All right, so let's build in that oscillatory function. So our goal is to orthogonalize. Let me zoom in a bit more so everyone can see this. There we go. Orthogonalize our bell curve like guesses, like wave functions. What we're going to do, whoever sits in this chair must be like a football player. What are you doing? I'm just going to climb on. Holy crap.
I think you're taller than the professor in the previous.
Oh, okay. Maybe he just likes his feet hanging.
I have a good time now. Yeah, just stop.
I think it's just broken.
Okay.
No matter. All right, so what we're going to do is basically we're going to write new wave functions. Psi prime of x. And we're going to take the bell curve part. So the bell curve part is 2k over pi to the 1/4 e to the minus kx squared. That's the normalized wave function we came up to in that last class. And we're going to multiply it by a special function, which I'm going to label h sub n of x times that. Right? This is a special function. Right? And this is our orthogonalizing function, which means oscillatory function. Right? And this is a special type of function. This math has been studied for hundreds of years. So the solution I'm giving you is not anything particularly novel or crazy. It just comes from the solution of this equation, which was studied way before quantum mechanics. People studied differential equations as early as the 1700s. So I think the solution is named after a man named Hermite, who was from the 1800s. It's old math. But these functions, hn of x, are called the Hermite polynomials, or the Hermite. I don't actually know how you pronounce his name. I like Hermite because he's European. It's very classy. Hermite polynomials. Okay, and they're special functions. You can look them up in a table. You can actually, there's an equation that generates them. We don't have to worry about that. I'm just going to write down the first couple of them. And the important thing is that, like waves, they have an integer. Like, remember a particle in a box. There's a n equals 1, n equals 2, n equals 3. We have the same behavior for the Hermite polynomials. They're quantized with quantum number n, call n. Yeah, I'm actually gonna name that something different later. I apologize. That's really bad labeling for me, but which can be which actually can be any number that's 0 or positive. It includes 0, right? That's new. We didn't have n equals 0 for the particle in the box. We went n equals 1. So we have this state now in our orbital or in our spring that has a 0 state. Right? We'll have to think about what that means, what a 0 state is. And the functions are very, very simple. I'll just write them down. H0 of x is a function. It's the easiest function in the world. It's the number 1. It's an easy function. H1 of x is 2x, also easy. H2 of x is 4x squared minus 2. And H3 of x is 8x cubed minus 12x. Right? They're just random polynomials. Strange. I just said that they're oscillatory functions. These are polynomials, not oscillating at all. Kind of an odd concept. But you can see that there's a pattern here, right? That the pattern is that the nth Hermite polynomial looks like x to the n. It's a polynomial of import. Now, you guys should know that polynomials don't oscillate. They go to infinity and negative infinity, or if they're even, they go to infinity, or they go to infinity at their limits. They certainly don't oscillate. So how the hell do I get oscillations when I multiply these functions? Well, as we'll see that oscillation, the concept of an oscillation is let's just say oscillatory functions are more promiscuous than you think they are, for subtle reasons. And in fact, these are oscillatory functions, but only oscillatory in a certain region of x. We'll see that. We'll plot some, right? We'll plot some and we'll see how they oscillate. Okay, so now we have a nice equation. We have a few more things that we have to do. We have to show that these are orthogonal to each other. We'll do that in a minute. But let me write down a general solution now for our wave functions. So let's just kind of put this all together. So the general solution, so what we have is a harmonic spring. All right. We have a special name for it. I'm not going to call it a spring anymore because bonds aren't spring, they're bond. This is what's called a harmonic oscillator. And I'll explain today why it's called a harmonic one. It'll be appreciated by the musicians in the room. Harmonic oscillator is one of the most important toy models in all of physics. One of the jokes in physics is that once you get to a certain level of physics, everything's a harmonic oscillator. And it's true. You guys learn in like intro physics, you learn everything about spheres or things that move without friction, the old spherical cow joke. That's how physicists come up with problems. Imagine a spherical cow that doesn't interact with other cows. Once you get to graduate level physics and chemical physics, everything is a harmonic oscillator. That's the way you represent the world. Harmonic oscillator. Anything that oscillates and emits radiation or heat is a harmonic oscillator. In fact, you can use harmonic oscillators and rederive all of thermodynamics. We go back and we can take this theory and just redo all of the first semester of this class if we wanted. We're not going to do that. Right? And so this has a general wave function solution. Right? We have a wave function psi. And I'm going to introduce a new quantum number. I called it n on the previous slide. I'm going to give it a new name, one that's general, that we use everywhere in science. We use the letter nu. This is what's called the vibrational quantum number. Sometimes people call it V for vibration. So V or nu, whichever one you prefer. Right? And it's a function of displacement, x. And it's equal to a normalization constant, which is 1 over 2 to the new factorial 1/2 times, I'm going to define this term in a second, alpha. It's a special constant that that's consisting of things that we've already seen, to the 1/4 power. And then we multiply it by our Hermite polynomial for quantum number v. Right? And the input of that function is not just x, but we scale x by alpha to the 1/2. So that's the input of the function. We'll do an example in just a second. And then we finish off the problem with our little Gaussian function, our bell curve. Okay. So let me just walk through all of these different terms. So V can be 0, 1, and onwards. If you guys don't remember, I'll write it over here. V factorial is equal to V minus 1, V minus 2 times 1, right? You just count down and multiply. Alpha is a constant. Okay. Alpha is a constant, and it's equal to the square root of k, the force constant, times mu, the reduced mass, over h bar squared. There's our h comes in finally. Right, so the wave function depends, again, the only thing the wave function depends on, other than position, is v, the force constant, the stiffness, and the mass, right? Nothing's changed, it's just the function it's not a sine wave anymore. But it depends on the same things that the classical wave function, or the classical function, depended on. And the last thing I want to write is that this is that the input to h is alpha 1/2 x. So the variable is alpha 1/2 x, not just x. All right, I'm just going to do a couple of examples. Let's just write some functions down. All right, so the wave function for the ground state, as we say, at psi 0 of x, right, is out. We've already written it. It's alpha over pi to the 1/4 e to the minus alpha x squared over 2. That looks sure like the guess that we wrote earlier. So the ground state of the we actually correctly guessed the ground state of the system by just saying it was a bell curve and then normalizing it. That's all that is. All right, so with our guess, we got the right answer. We just only got one of the infinite states. And we need the orthogonalizing function, the Hermite polynomial, to get the other ones. This was a perfectly reasonable guess, because it's in fact the correct answer for the ground state. Psi 1 of x is 4 alpha cubed over pi to the 1/4 x e to the minus x squared over 2. I missed an alpha, sorry. This is alpha x squared over 2. Right, you can see now I'm starting to get that Hermite polynomial coming in. I have an x now on the outside. What that's going to do is change the sign of the bell curve from positive to negative as you go around x equals 0. Interesting. Right, now we're going something that oscillates from negative to positive. It's got a sign change. And we'll just do a couple more. I'll just do the next two. Psi 2 is alpha over 4 pi to the 1/4. Then our Hermite polynomial is 2 alpha x squared minus 1 e to the minus alpha x squared over 2. And then finally, psi 3, our third level, or fourth level, excuse me, is alpha cubed over 9 pi to the 1/4. Kind of a funny number. You don't see 9 pi very often. That's just the way the math works out. 2 alpha x cubed minus 3x to e to the minus alpha x squared over 2. So we have, again, the same basic solution in all of them, some number times the bell curve, but we've appended a polynomial in the middle. Right? Each level has an increasing polynomial of increasing order. All right, and so those should theoretically cause these to be orthogonal. Meaning if I take psi 0 times psi 1, I get a function, I get an integral that is 0, right? Which means that we're orthogonal. I'm not going to do that math. It's just a waste of time, but I can show it to you graphically. All right, let's think a little bit about what these functions look like in space. This is always positive, right? E to the minus x squared is always a positive number, so this is always positive. It's a bell curve, actually, after all. This one over here is positive when x is greater than 0, but negative when x is less than 0. This one's positive everywhere because you have an even function bell curve, an x squared, a parabola that's even. And here we have an odd function. We have x and x cubed. Those are very odd times an even function. Right? So we have the symmetry changes that we expect. Even, odd, even, odd. They alternate just like a particle in the box. All right, so let's look at that. Let's just make a little plot. So we're going to make two different plots. And I want to plot psi of x here and psi squared over here. Right, the probability. Right, I'm going to draw two different potentials. One for each one. It's identical potentials. Here's our potential for one. And I'm going to draw the same potential over here. Like that. That's a terrible picture. Right, so here's our potentials. And I want to, geez Louise, there we go. Much better. Okay. There's my two potentials. And what I'm going to do is I'm going to draw my energy levels, my wave functions as at different levels of energy. All right. So on the y-axis, actually, let's just do it like this. The y-axis, we'll start with nu. Right, and we'll say that we'll write 0, 1, 2, and 3. Right, but the question is, where do I put those energy levels? I haven't calculated the energies yet. So I'd like to be able to put wave functions here. I'd like to measure the energies of the wave functions, but I haven't even calculated. This will be a homework question. I think I'll add on the next problem set. But the energy equation for harmonic oscillator is the simplest damn thing in the entire world. Right? So the energies of the harmonic oscillator are quantized by the number v, the nu again. Right? And the energy is equal to h bar times omega, the frequency, v plus 1/2, nu plus 1/2. Where omega is the same spring constant we had before, a over mu. I mean, how easy can you get? Right? Way easier. Remember in particle motion, a squared, n squared over 8ml squared. That was a miserable. I mean, it's not a miserable equation, but it's got a lot of numbers. This has three numbers in it. It's got h bar, that's just a constant. It's got two parameters. It's got the quantum number and it's got nu. That's it. Let's look at this. Let's look at this behavior a little bit, right? Where are these energy levels now? All right, so what I'm going to do now is I'm going to draw energies on this diagram. Right? So where is the E equals 0? Where's the 0 state, the ground left state? Oh, that's V equals 0. Notice that the energy of the V equals 0 state is not 0. From this definition, it says that the ground state energy is 1/2 h bar omega, which is not equal to 0. Okay, so if I put over here 0 for V, I have an energy level here. Okay. And on the other graph, I'm going to put another axis here. Then this will be energy instead. And that is at h bar omega over 2. Notice that the energy of the vibration of this molecule or this bond is never 0. There's always some energy in it. So it doesn't matter what I do with a bond. I can cool it. Well, I can't cool it down to 0. And the reason why I can't cool it down to 0 Kelvin is that no matter what I do, the minimum amount of energy that a bond can have is 1/2 h bar omega. It can never be 0. So this, in some senses, again, proof that the third law of thermodynamics, which is that you can never go to absolute 0, it's impossible to reach absolute 0, is inherently true. Because if I had an ensemble, a sample of just diatomic molecules, and I cool them down to as low as possible, there's always still a little bit of residual heat in them because their ground state energy is non-zero. There's always residual heat in a bond. What that means is that even at effectively 0 Kelvin, the bond is always doing this. It always is vibrating. Always vibrating. That's a strange problem. Very not classical. Obviously, a classical spring can have 0 energy. There you go. It's got 0 energy. Right? If I did that to a molecule, threw it down there at cold, no energy whatsoever, it's going to sit there and do this the whole time. And I can never stop it. Kind of a crazy idea. We're going to look at the consequences of that a lot. This is a universal concept. Anything that's what's called an oscillator in quantum mechanics always has residual energy. It never has 0 energy, by definition. This is a consequence of the Heisenberg uncertainty principle that we can't know position and momentum at the same time. I'm not really quite ready to make that argument to you yet, but that's the consequence of this. The idea is that the spring always has some energy. And we have a special name for this energy, what the chemists call it. Well, the physicists do too. It's called 0-point energy. Right. We'll explore the consequences of 0-point energy in this class after spring break. Okay. All right. So there's our energy. Let's just draw a couple more on our graph. Right. I don't really need to do much here. Right. E1 is 3/2 h bar omega. E2 is 5/2 h bar omega. And E3 is 7/2 h bar omega. Right, so the easiest equation in the entire world. So I can go ahead and put those on my graph. I've got 1, 2, 3. What's the energy difference between these levels? You guys may have saw on the current homework that in the particle in the box, the gap between adjacent energy levels gets large. Because the energy scales as n squared, the difference between n plus 1 and n, once you do the foiling, is 2n plus 1. What that means is that the spacing between the energy levels in the particle in the box is dependent on the value of n. As n gets bigger, the spacing gets larger. That's not true here. What's the spacing between these? E0 and E1 is different by h bar omega. E2 and E1 are different by h bar omega. E2 and E3 are all different by h bar omega. Every single level in your harmonic oscillator is spaced by the same amount of energy. You have a symmetric ladder of energy levels. They're all spaced by the same amount. This is why it's called a harmonic oscillator. Right? Think about what harmony, the concept of harmonics in music or acoustics. The harmonics of a note are the doublings of their frequencies, right? A440 is the first octave. You go to the next octave, go to A2, which is at 880. Right? You space it by 440 hertz. You go to the next one, you add 440 hertz to 880, get the next A note, and so on and so forth, right? Every A note, every octave is spaced by the same amount, which is the frequency of the note. What is the frequency of a note? Well, we just talked about last time. It's the oscillation of a specific spring of a specific stiffness and a specific mass. So you have a harmonic oscillator. A harmonic oscillator is a piano string that's tuned to a specific frequency and set so that you hit the same note as you double the frequency. Every note, every A note, every octave is spaced exactly by that amount, the frequency. Exactly like we have here. You can kind of think of this as being A440, and this is A880, and A1320, and so on and so forth. And so they're equally spaced energy levels, which is why we call it harmonic. So it's the harmonics of a fundamental note, which is omega. It's a nice little system. It's amazingly beautiful how simplified this goes, right? We took a really complex spring with a bunch of forces and kinetic energy and wave functions and all that, and everything simplifies down to a energy level spectrum that's equally spaced and only dependent on the same parameter that sets the frequency of the classical spring. There's no added complications. It works exactly the same way as a spring does, except a spring can have any energy. Right? You can set your spring to be A, B, C, D, E, F. But a quantum mechanical spring, if it's A, it's always A. Right? And it scales as the octaves. All right, so let's draw some functions here. Let's go back and look at our wave functions. Erase this so I have some space. All right, so let's just go one by one. Oop, okay. That was not the direction I wanted it to go. Oh, shit. Oh, it's freaking out, man. Okay, sorry. All right. Oh, geez, Louise, this is scary. It's going to go crazy. Okay, so the first function was a bell curve, right? V equals 0 is just a bell curve. So we can draw that just by inspection. Right? Remember, a bell curve doesn't decay to 0 except at infinity. So I'm just going to draw some lines on the exterior so that I can draw the function outside of the potential. And the potential, it's going to peak at the middle of the potential and then decay to infinity exponentially at the edges. Like this. And then psi squared, we're just squaring an exponential, which means you just get a factor of 2 in the exponential. So you just get a Gaussian bell curve for psi squared. It's just more compressed because it decays twice as fast. So this one would look like, we'll do it this color, right? A little sharper, something like that. Okay. So what does this tell me? Well, this tells me that the length of the bond has some average length. It's right in the middle of the potential. at the equilibrium length, but it has some distribution, meaning that when you measure the bond length, there's some standard deviation to it. Sometimes it's shorter, sometimes it's longer. And sometimes it's even outside of the turning points. Next class, when we come back, we'll actually calculate what that percentage is. What's the likelihood of seeing it outside the turning? Right, but it's an even function. It's not super interesting. Right, let's look at the second function, right, for the first level for v equals 1. And here it is here on the right, right? It's the same function, but we've appended an x to it, right? So what that does is it makes the function go to 0 at x equals 0, and then it's negative at negative x and positive at positive x. So now we get a sign change in the system. Why is it doing that? Right? So we know that in the center, it's 0. And then the function grows as x, and then it decays as e to the minus x squared. So it's going to kind of peak up like this, and then decay out. And then the other side is symmetric, but negative. And like this instead. That. And so when we take the square of this, it becomes even again. And now it has 2 lobes. Okay. Now maybe you can start to see why these two functions are orthogonal. Right? If I multiply these two together, I get an odd function. Right? The integral, right? I get an odd function. So this one, so what this does is it goes to 0 here. You get a negative end and a positive end. We bias the wave function to become odd, so the overall product is odd, and therefore it integrates to 0. Okay? So that's why they're orthogonal, because of the sign changes that the polynomial gives. So let's just keep going up one more. The next one is x squared. But the important thing is that it's x squared. There's a slight change, but it's 2ax squared minus 1. And so that means it shifts the function very slightly, but it makes it even. And so because of that, it's going to be, because of the x squared minus 1, it's going to be positive on the sides and negative in the middle. So in the middle, it looks like a parabola starting at x equals minus 1. I'll draw it like this. Right? And then it's going to decay like e to the minus x squared. So it kind of looks like a parabola in the center. And it comes up and then decays off at the tails because of the exponential tail. And if I draw the psi squared for this, you can see it starts to look 3-necked sine wave. Right? And then the final one, it's not too hard to calculate, but it basically goes negative, positive, negative, positive. So psi squared looks very similar. Hump, a bigger hump, an even bigger hump, smaller hump like that. Now do you see why they look oscillatory? And even though they're polynomials, they oscillate like sine waves inside the potential. Right, so they have the local behavior that we want, right? Remember that we want wave functions that oscillate like waves inside of the potential and then decay exponentially outside of the potential. And that's exactly what the Hermite polynomials give us. Is they give us first at v equals 0 a wave of half period, right? It's just one half phase of a wave. At v equals 1, we get a whole period. At v equals 2, we get a period and a half. And v equals 3, we get 2 periods, just like the particle in the box. So the polynomials introduce, or sorry, they introduce that oscillatory behavior we want, but they're not sine waves. The reason why we can't use sine waves is because those oscillate out to infinity. Right? We don't want oscillations outside of the potential. The potential needs to decay exponentially. So the wave behavior of a spring should only occur inside the potential. So it cannot be a sine or a cosine. Therefore, we use a local approximation for a sine or a cosine. And that turns out to be a polynomial, right? Through the Taylor expansion, Taylor series. There's some other math that goes along with it. But the idea is that if you want a local sine wave, something that oscillates in a small region of space and then stops, polynomials do exactly what you want. So we have wave-like behavior. Exactly like we want. Okay. I want to do one more calculation, then we'll finish a little further. I don't want to get too deep into this because then I want to come back and I want to apply this to molecules. We're just talking about generic springs today. Do I want to solve this right now? Yeah, why not? Let's do this problem. Okay, what I want to look at just to finish up is a little example. I just want to work with these wave functions a little bit. And let's imagine I have my spring in its ground state, B equals 0. And what I claimed, remember in classical physics, my spring, when I give it some vibration, it never goes past the edges of the potential, right? Spring moves from this point to this point and backwards again. Right? It ends at the edges of the potential. But the way I've just drawn the wave function for this system is it decays outside the potential. It has to because it's Gaussian. It only goes to 0 at infinity. So my question is the quick thing I want to calculate is what's the probability that we find it outside of the potential, right? In other words, in psi squared, what is the area under the curve out here? Right? In some sense, this is the interior. This is the probability of finding the bond in the classically allowed region. Those are if the bond were an actual spring, those would be the positions that it would sample. But there is some ability for it to be outwards as well. So let's go calculate what that is. We have everything we need for it. We have wave functions, we have energies, we have potentials, solve everything we want. So let's do that. It's a really simple calculation. Okay, so let me just redraw. Let's just set up the problem really quickly. My potential. I have no idea why my thing went really thin. It was really thick and now it's not thick. I think it's telling me we got to go home on spring break. So I'm done at this point. So this is x equals 0. And we're gonna look at something and its vibrational ground state. All right, let me give it this different color. Okay. So we're gonna put our system at v equals 0. Zoom in. Okay. Okay, so we have a wave function. It's a Gaussian. Right? Looks like this. And I want to look at the probability that it's outside the potential. All right, so I want to integrate this space right here. Okay, so what I need to calculate are where the turning points are. Where does the wave function intersect the potential? I want to calculate the turning points. Right? If I know that, then all I need to do is integrate from the turning points out to infinity. All right, so we're going to call this point x plus and this point x minus. Those are the turning points. Okay. X plus appears where the energy of the vibration E0, which is 1/2 h bar omega, right, is equal to the potential, which is 1/2 k x plus or minus squared, right? I want to see where those two things match. right? 1/2 h bar omega is my horizontal line, the yellow horizontal line, and I want to see where it intersects with the potential. Okay, well, that's really easy to solve. Omega is square root of k over mu. So what we get is that okay, so now what we're going to do is we're going to damn it, what do I want to do? What's going on here? Okay, so now I have to our wave functions are have units, or sorry, have dimensions alpha to the 1/2 x. So I need to scale my x coordinates. So I'm going to call it x prime is equal to x over alpha. And what I can show is that x prime plus or minus is equal to the square root of, let's see, v plus 1/2 is 1/2 2, so it's h bar omega over alpha squared k, where k is the force constant. Okay, and then we have that omega is equal to k over mu, right? So we can plug that into this equation, and what we get is that x prime plus or minus is equal to 1 in these units, okay, for v equals 0. All right, so that's really nice. So that's why one of the reasons why we scale the dimensions of our harmonic oscillator with this alpha to the 1/2, it makes this unitless. The units of x are alpha to the 1, are inverse alpha to the 1/2. So this has units of our unitless, the unitless direction, or displacement. And so it just, once you put in v equals 0, everything just beautifully simplifies that the turning points are at plus or minus 1. Right? So that's like really, that's just, the math works out really nice. And that's why they chose to scale the coordinates by alpha, because it simplifies the math out very nicely. Okay, so that means then the probability that spring is past turning points is going to be equal to the integral from -infinity to -1, that's this region right here, of psi squared, psi 0 squared dx, plus the integral over here on the right, which is the integral from 1 to infinity of psi squared dx. Okay. Sorry that this is so, I'm going to change colors in just a second. But this is an even function. The right-hand side, x greater than 0, is the same as the left-hand side. So these integrals are the same value. I'm just doing the same integral twice. So this is equal to 2 times the integral from 1 to infinity of psi 0 squared dx. All right, we can plug that in. That's going to be equal to, once you do all the math, 1 over pi to the 1/2 integral from 1 to infinity e to the minus x squared dx. I did some u substitution and stuff, and that's what you get. I'm sorry, I forgot a 2 here. It's 2. Is that because there's 2 of them? 2. Okay. So this integral turns out to not be something that you can solve analytically. It's what's called the error function. So a special function in engineering and science. This is called, so I'll write it down here. The function integral from x, sorry, we'll call it from, x to infinity of e to the minus y squared dy is called the error function, ERF of x, error function. Right? It's a special function. You can look it up on Wikipedia, and it like statistics books have it tabulated. Right? It's one of those functions that are tabulated. And so you can look up the value for this, and it's equal to 0.0157. So what does that mean? That means that the spring is past the turning points 15.7% of the time. So 50% of the time, a spring is breaking the rules. Exactly 15%. This has very, very deep consequences. Why does it have deep consequences? Well, let me set up an interesting potential. I want you to think about a bond that's moving on this potential I'm about to draw. And you'll maybe start to understand why it may be important or consequential that the bond may be longer or shorter than you would expect last. Imagine you have a reaction A to B. All right, and we're going to treat it like you're breaking a bond and replacing it with another. Okay, and so you could think that we could draw a little coordinate system. So this is the reaction, and we can do it as a function of energy. And we'll say, for instance, that B is here in energy and A is here. Okay, so what I can do is for that bond that's reacting, I can draw a potential energy diagram that tells me the energy of that bond as it stretches. Maybe it's better to think about this like this instead. AB plus C goes to AC plus B. I think that's a better reaction for this. So this is AC and this is AB. Okay, so what I'm going to do is I'm going to break AB and then replace B with C. All right, and what I'm going to assume is that the AB bonds and the AC bonds are harmonic initially. Right, so they have a harmonic potential, which is a parabola. But eventually, B and A are going to stretch so much that it breaks, and C is going to come in. Okay, so what we can imagine is that we have a potential energy surface that looks like a parabola, but as it starts to stretch, it rolls off, and then it decays like this. Okay, and so this is the transition state down here. This would be something that looks like B, A, C, right there in the middle. Okay, and imagine I get this reaction to start going. I pump it in with a little bit of energy. Right? I start with AB with a little bit of energy, and let's just say I don't have enough energy to get over the barrier. Right? Let's try a couple of different examples. All right, so maybe I have energy here at V equals 0. Right? What does the wave function look like in this potential? Well, it looks like a V equals 0 harmonic function. Right? It's a Gaussian function. Right? And it's got some ability to escape the barrier or escape the well. But by the time I reach the other side of the barrier, basically the probability that the bond that is that long is 0. Right? So the probability here is about 0. Okay, so what we say is that this system is fairly localized in AB. Right, the system is mostly just AB. There's no way for it to really escape because there's no probability of it passing through the barrier. Right, but what if I put the energy really, really close? Like right there. All right, we'll say this is V equals 4 or 3 here. I've pumped the energy up and I've given it an infrared photon and excited it to V equals 3. And this function also decays out. right? But now there's a little bit of potential, non-zero probability, right? That the system can actually go through the barrier, right? There's some probability that the bond may actually be in the region where A and C are, right? And so what I have every once in a while, every time I measure the system, there's a possibility that I find the particle over here. So sometimes it's here. I have AB here. It's kind of sitting, and maybe C's coming in over here. Hold on, let me draw it. Maybe C's coming in over here. Okay, on this side. And then on this side, I have something that looks like AC with B leaving, like this. And so because the wave function extends through the barrier here, a system that's initially localized into this structure here, AB, may end up, when you measure it, end up being CA. Right? So sometimes it happens to end up on the other side of the barrier just probabilistically. It moves through the classically forbidden region and it ends up on the other side just by luck. It might be 1% of the time, might be 1/10%, it might be 1/millionth of a percent. But if you've got a mole of molecules and there's 1/millionth% chance of this happening, you're still going to make a millimole, a micromole of material that just tunnels through the barrier, they call it. And so if the molecule ends up on this side, on the right side, right, the system now is over here, just spontaneously, it's now over there. It doesn't have enough energy to get over the barrier, but because of the probability through the potential, the system appears on the other side of the potential barrier, and then it just cools down to form A and C. Right, so what this is that because bonds are leaky, they can travel through barriers through a process called tunneling. Okay. And you can observe this tunneling process in actual reaction, right? I'll talk about an example of this next class when we come back to class, of where you can actually measure this tunneling rate, where you can show that the object doesn't travel over, the molecule doesn't travel over the barrier like a normal reaction, but it goes directly through it. Doesn't have enough energy, but it still travels on the other side. And there are certain experiments you can do to show that that does happen. Right? This is most commonly seen in chemistry. Not everything can tunnel. It has to do with the mass of the object. The heavier the mass is, the more damp the oscillation is. So light things tend to tunnel really effectively. So notorious tunnelers, sounds like a hip hop group, are hydrogen atoms, right? And electrons. In fact, electron transfer, the process of electron transfer is a tunneling process. Right? So those are the most common things, H atoms, electrons. Another thing are helium atoms can also do it as well. Very common for helium atoms to tunnel. But electrons and hydrogen atoms in particular are the worst case scenario. Hydrogens just love to tunnel. A great example of a tunneling reaction in hydrogen, a hydrogen example, is what's called the 1,3 shift, which is this reaction. Where this hydrogen, I'll mark it in purple, goes from the left side to the right side, and then the allelic group. So like a radical, it could be a plus charge. Maybe it's more common if it's a plus charge. Put a plus charge here instead. Right. You can show very easily with both some NMR and some other work that this occurs through tunnel. It doesn't go over the barrier at all. The hydrogen actually just tunnels between states. So it turns out that, like, if you look at the rate of this, the observed rate, with hydrogen, the relative rate is 1. If you replace it with a deuterium, you add an extra neutron, you make it twice as heavy. The rate is around 10 times slower. Okay, so with hydrogen, it tunnels at some rate, and then you add 1 mass to that deuterium, making the weight on the end of that spring heavier, damping that spring and lowering the probability that it goes to the barrier more because it's damped. It changes the reaction rate by a factor of 10. I have a really cool example of a reaction where the hydrogen tunnels, where the rate difference between hydrogen and deuterium is a factor of over 1,000. 1,000 times slower. Because the reaction doesn't occur. It doesn't have enough energy to get over the barrier, but it has just enough energy for the hydrogen to tunnel. And then when you add a deuterium, it turns out it lowers the energy of that system just enough, and it slows and dampens the spring out just enough that it now reacts 1,000 times more slowly. Really, really cool process. So I'll show you some examples of that after. We'll look at that next class when we get back from break. Okay, that's all I got for you tonight. Have a good one, guys. Have a good break. See some of you tomorrow.